Thanks for a nice introduction. Now we have our keynote speaker, Professor Philippas Segas. It's really nice to have him here. He's kindly agreed to give a keynote speech. So let me read out his biography, brief biography. So Professor Philippas Segas is currently a professor at Chalmers University of Technology, Sweden. Professor Segas received BSc degree in mathematics and PhD degree in computer engineering and informatics from University of Patras, Greece. He has held positions in National Research Institute for Mathematics and Computer Science, CWI, in Amsterdam, the Netherlands, the Max Planck Institute of Computer Science, Saarbrücken, Germany, and Uppsala University, Sweden. So this is about his background. His research interests include concurrent data structures and algorithms for multiprocessor and multi-core systems, power-aware computing, fault-tolerant computing, autonomous computing, and scalable data streaming. Okay. And he's a co-recipient of Best Paper Awards in IEEE IPDPS 2003 and 2021. This just happened a few months back. Okay. And ACM DEBS 2017 and ACM SNS 2012. Okay. So nice. That's really nice achievements. And he publishes in conference, like several conferences, ACM CHI, IEEE Infobis, ACM PodC, DIS, COPODIS, SPA, IPDPS, DEBS, ECSA, and so on. Okay. So this is his background, and it's really nice honor to have him here. So without further delay, so Professor Segas, I see you here. You can start your keynote speech. Thanks. It's really nice of you to have you amongst us.
Thank you, Satya, for inviting me. It's a great honor. Let me first see if I can share my screen right. Okay.
Yeah, we can see it.
Okay, excellent.
So you may have to change it to full screen mode, though. Yes. Yes.
Is it okay now? Everything okay? Yeah. Excellent.
It's good. It's good. It's good.
Thank you for the invitation. It is a great honor. At the beginning, when I received your invitation, I was thinking of talking a little bit about concurrent data structure. We have been working for quite some time now. But then I realized that maybe for the looking a little bit at the conference, that the fact that talking about machine learning, maybe it is of interest, and maybe it fits better. So I decided more or less to talk about parallel stochastic gradient descent, and talk a little bit about the work that we are doing in this direction. And I must say that in fact, slides and work has been jointly done with Caleb Beckstrom, Ivan Valulia, or Marina Papatriotafiliou. And this work is supported by the Wallenburg AI Autonomous System and Software program that we have here in Sweden. And as I said, this talk is going to be about parallelizing stochastic gradient descent. So my plan at the beginning was to talk a little bit about, first of all, was to give you a little bit of a motivation. Why do we care about parallel stochastic gradient descent? And what is it exactly, the approaches that are in the literature? And what we are trying to more or less improve, what are the evaluation metrics and benchmarking that we use in order to look into the efficient solutions and evaluate efficient solutions for parallel stochastic gradient descent. And at the beginning, I was thinking to talk to you about two things, about a bit of the work that we do here with at our group on looking into consistency and log freedom in parallel stochastic gradient descent, and how consistency and synchronization influence the speed and convergence of stochastic gradient descent. And I was also thinking also to talk a little bit about the adaptive synchronization as maybe a consequence of this work. But I don't think I will have the time to do that. So maybe some other time. And so I will skip that part. And so that I will not talk about adaptiveness today, I think, but I will focus more on the consistent and synchronization issues. And I will conclude at the end with some concluding remarks. Feel free to interrupt me as I talk. So, yeah, let me start. So probably you have all. It is very well known that in fact we live on a data era right now. There are estimates that in fact we are right now there are more than 44 zettabytes of data stored in all devices. And if you look into the a little bit into the trend, then we expect that we have we had by the end of 2021 approximately 14 billion I2 devices outside there, and then and on top of that we had also 10 billion devices that are computers and telephones. So, and all these kind of IT devices are, as you know, are expected to bring us more and more data that we should try to make value out of them and try to understand better the different aspects of our lives, our industry, our work, and our environment. So we are more or less all this kind of data give us now the opportunity to use them. And of course, in order to use them, we have to derive analytical methods for doing that. And then in order to do that, we use machine learning. So, and then you can, there are different machine learning algorithms. You can use linear regression sometimes, you use matrix completion algorithms, you use artificial neural networks or deep learning networks and algorithms. So, and if you look into all of them, then they have a big problem with this kind of big data sets that they have to process. Computationally speaking now, the amount of computation needed increases with the amount of data that are outside there. So, and in order to scale with the data, to manage to process all this data, parallelization was proposed as a way of coping with the large data sets. So there is a big trend about then going into parallel and distributed algorithms for machine learning. So, and this talk is about parallel, the component of the parallel processing for machine learning. And you can think that in fact there is this kind of trend of going first parallel as much as you can, then and then going as much distributed as you can afterwards. So scale in and scale out, it is words that you might have heard on machine learning. So, and we're looking now into all these methods for algorithms that you find for machine learning. They have something. They work like that. You are on a high level. They take the training data, and then the machine algorithm is trying to build a model out of the data. And this model, we will say that it is the model theta. And they try to most of the times they use stochastic gradient descent in order to find a good model, in order to optimize the model, and end up with a good model. And I will come back to in the next slide what a good model is and how it is used. So what I want to say is that the stochastic gradient descent, when we looked into the machine learning algorithms, was a very popular backbone. It's the backbone also of ANN training. And the question that we wanted to look at was like, okay, how do we parallelize stochastic gradient descent? So, and let's come back again into the machine learning and how stochastic gradient descent is used. So, on again, on a high level, we have, as I said, a data set. And what we do is that we want to derive as a model. And we want to have that this model is more or less explains the data and recognizes the patterns on the data. And in order to do that, we have to come up with an error function that more or less will tell us that if I have a model, how far this model is to the data set that I have. So, and this is, let me see if I can help. Okay. Laser pointer. And here is you can see that you come with a model, and then you have to define an error function that will tell you how far your model is with respect to the data set that you have. And you want iteratively or most of the times you go iteratively and you improve your model so that in fact you minimize this error and you have a better and better model. So, and in order to minimize this error function and find a better model, then the machine learning algorithms quite often use the stochastic gradient descent. That is an iterative method that starts with an initial model, and every time it adjusts the model using the negative gradient of the error function that constitutes the direction of steepness descent that will result into a trajectory corresponding to the slope of the target function that will lead you to the minimum value of the error that you are looking for. And this is, as I said, as an iterative function, and with there are a couple of parameters that I have to explain here. Is that when you adjust and first of all, when you compute the error, when you use stochastic gradient descent, you use not the full data set in order to compute the error, but you use a subset. So B is a subset of D, and this gives the stochasticity, and we call B a random batch of the data. And there is also this multiplicator factor here for the gradient descent, and this is the step size, how much you're more or less using the gradient in your computation or to adjust your model. So, any questions? So regarding that, this is what a stochastic gradient descent is. It's a very simple iterative method for optimization. And the one that I explained to you is the sequential version of it.
So that the way question I have is, it seems to suggest very sequential, right? So theta plus 1 depends completely on theta, right?
Yes.
So it seems to, I thought it's hard to parallelize, right? It seems as if it's hard to parallelize. And this FB theta function is a standard function, right? Stochastic function, the FB of theta.
Yes.
Yeah. Yes. Okay. Fine. Thanks.
So as Satya mentioned, that in fact the interesting part about this algorithm is that for us is that it looks very sequential. So it is a big challenge, right? So that's I mean, coming from the research perspective, then when you see it, say, oh well, this is very sequential. How do you parallelize? And then that's also what attracted us, and also we will see a little bit of the trends. And I hope that I cover it. I managed to cover it today. So it's a very sequential algorithm that goes into rounds, one round at a time. That's very good. And one other thing that we should also have in mind is that, in fact, there are parameters that you set. So what is the step size, the granularity, and what is the random batch size? And this plays a significant role in, when you look into the literature, plays a significant role into the convergence of the stochastic gradient descent. And there is a lot of literature that also look into these kind of parameters. There is also a lot of research, practical research into this direction. And I think these are two observations that will guide us a little bit into this kind of research. So in our research, we'll also try to understand the sensitivity of the parallel stochastic gradient descent to the different hyperparameters. And we will look also into then again how to parallelize anyway a sequential algorithm. So Then yeah, the challenge is how to make that. In fact, it's not trivial to parallelize, as I said, and then there are two options on a high level, and the two options says that when I try to parallelize, I have to bound the parallelization to keep it as close as to the sequential SGD, stochastic gradient descent algorithm, in order more or less to have a prediction of how the parallel is going to work. That's one technique, and that in fact it is this technique is covered by what we are going to see as synchronous parallel SGT. And there is the other technique says that if I go synchronous, I will not really parallelize it that much. And of course, I will have a behavior that I can more or less easily describe it. But on the other hand, I will not parallelize it. But if I go and increase parallelization, I have to start looking and relaxing the semantics and the constraints of SGT, and then I will have different behavior. And then, but this is challenging. But then on the other hand, this gives us a lot of nice research to do. And in fact, in my presentation, I will talk quite a lot about this, of how to increase parallelization by relaxing semantics and looking how these semantics are influencing the behavior of SGT. Okay, and I'm spending quite a lot of time on the introduction, so I have maybe to speed up. So in order to make sure this is for, I will assume today I will talk only about parallel system. So the system model is a model where we have M concurrent asynchronous thread. M is the number of threads, and we have a scheduler that is responsible for interleaving the steps, so and making the schedules, the asynchrony, and defining the way that the processes are executing. And then in this kind of system, I will assume that we have atomic operations that are common on the set memory systems. I will assume that I have operations like compare and swap that reads and modifies the content of memory, like one memory location in one atomic step from hardware. I will skip that. I will, and we are going to look into properties. I will not say a lot, but I will say that we'll look a little bit in properties like log freedom and wait freedom, but probably I will not go into detail into that. Okay. So, and before starting talking about synchronous and asynchronous parallel SGT, in order to see a little bit the metrics that are used in optimization algorithms that are recursive and like stochastic gradient descent and that work into rounds, in the literature there are three measures that are used. So the first one is called statistical efficiency, and then it counts the number of iterations until you reach what we call eco-vertex, or until you reach an error of your model that is smaller than epsilon. Then you define the epsilon. So it is how many iterations, if you have a sequential, then you say how many iterations you need until you reach the quality of the model that you are shooting for. And then another measure is that, okay, the number of iterations per whole clock time, or more or less it tries to say, okay, how much time do I spend for each iteration? How big is every iteration? You can have many iterations that take a lot, not a lot of time, but you can have also a small number of iterations that each iteration takes a lot of time. So the computational efficiency counts how big time each iteration takes. And in fact, at the end, what people care mostly about is the overall convergence rate, which more or less counts the whole clock time until you reach the quality, the convergence that you are looking. And in fact, the convergence time is it is the product of the statistical efficiency times the computational efficiency. So these are the measures, but they are interesting to look into each one of these two first because they you can have different designs based on what you want to maximize. Do you want to maximize the computational efficiency, or yeah, how much statistical efficiency you want here? So, any questions regarding the evaluation metrics? And so, if there are no questions, then let's look into a little bit into them now, into the landscape of parallel stochastic gradient descent. So you can think that in fact we have.
Just a minute, can I interrupt? Just a minute.
Yeah.
This the rate of convergence, how sensitive it is to the computation of error. You told that theta and subscripted the B, the data set subset. So the rate of convergence, does it have any relation to estimating that?
You mean the error function, or
the function that that theta? The slide you can go back. The theta subscript B. B you told that is a subset of D.
Mm.
Yeah,
Yes.
this is random
Yeah, but at the end you have to use the D after the computation. So the last convergence, it has to be on D.
Yeah. Yeah. So the choice of B, because it is random, so how does it have any impact on this rate of convergence? Are they biased data set? Do they have any bias?
There are different methods to use, but then the idea is not to have you can use a bias if you want, but it plays a role. But at the beginning, we assume that it's completely random. There is no bias. So this is what I will assume now.
Okay.
And definitely, yeah, this brings the stochasticity that has been shown to be good in the general case. But if you have knowledge of the data, you can change. You can definitely make use of it.
Okay. Okay. Thank you.
You're welcome. Thank you. And at the end, the final convergence is on D. It's not on a you start with on a B. Okay. So going back into the models, as we said, you can think that in fact, yeah, if you want to go and parallelize the stochastic gradient descent using a synchronous way, then what you have to do is that you have to more or less give different batches to the different processes, and then they will compute their gradients, and then they have to do one round at a time, and then they will have to come and merge. And if you look into that, then you have all this white space that is wasted time, right? So, but on the other hand, as we're going to see, this is if you do it synchronously, then you will have a very nice behavior that it is easy to argue about. If you do it asynchronously, what you want to do is that you allow the processes to go asynchronously, and then you have here thread 1 that finishes the first round, and then you can start the second round before all the others have started this round. But as you can think now, there is nothing like a round that you can describe as a single round. So the rounds are intermixed, and there is no single round of the full algorithm. So if you look into the behavior of the synchronous algorithm, then what will happen is that if you have now m, as we said, threads, then the M threads will start. They will read the model theta that we have, and they will start at time t, and we assume that this is the t iteration that is starting. Will read at the model theta t, and then they will go and compute their gradients, and then they will use different batches of data, and then they will compute different gradients, and then in the end they will aggregate the gradients, and then we take the average of them, and then at the end of the round we can write and update the model, and we have this theta t plus 1 model. So if you look into that, then and you do it like that in a parallel system, what will happen is that what you're going to end up is that you're going to end up with a model that is will be described like that. So the difference now it is that we have instead of the gradient descent of 1, then we have the average of all of them. But in fact, in reality, it is very similar to the sequential one. And then this calculation is approximately the same as having a bigger, having a sequential gradient descent algorithm, where in fact the batch size is the union of the micro batches of the different processes. Is it clear? So by doing it in a synchronous way, you end up in fact in a very similar behavior with the sequential one, where you have increased the batch size in each round. This is in fact not good, because by increasing the batch size, if you go with a synchronous parallelity, it has been shown that by increasing the batch size, in fact, you are ending up with less stochasticity, and then you're ending up with a lot of bad convergence scenarios. So the outcome for that is, what I want to say is that you go and you have a synchronous parallelity, you conform to the sequential semantics, you have very nice predictable performance, but on the other hand, you don't have good scalability, and in fact, the processes that are finished first have to wait for the other processes that are slow, because they have a batch data that are difficult, that are more complex to compute with.
So let's look one interruption. So in the synchronous model, are you using barriers to synchronize or using fork join approach?
You can do both, but barriers is a typical way of using it, because barriers are also quite efficient.
Efficient, okay. And other thing is, mathematically, this has been shown. This is approximately same. This summation is approximately same as the delta FB into M, right? The reverse.
Yes.
Okay.
Yes. Yeah. So it is approximately this, and it has been observed also in the literature. And in fact, we have there is quite a lot of work, and in fact, this is also the problem that has been also by many papers, and from one of us also, that look into that. This gives scalability problems. That in fact, by increasing the number of processes in a synchronous system, you are increasing the batch size, which means that you are lowering the stochasticity, which is a problem on the synchronous model. Any other questions? Or
but the delta is always positive. This delta, the gradient, that is delta is always, it is a positive number.
This delta is your
it's I mean, it is a slope. The slope is always positive, or it could be negative also.
if you want to minimize, you're taking the minimum the positive. So that it more or less depends if you want to maximize or minimize. Yeah, and if you're not if you are not getting a positive, that means that you cannot improve. If there is no positive from this data set that you have, that you reach the local minimum in this case.
Okay. Thank
you. So then let's go into the asynchronous parallelizity. So if you look a little bit into then how an asynchronous parallelizity is going to look like, then you have now again the same setting. We have the model stored in the shared memory, and then you have that one process reads this model and computes the gradient, and then wants to go and update. But now, because you allow asynchronous processes to go and compute their own gradient, so you might have that during this time where a process computes the gradient, there are other processes that have read before the model, and they come and update the model. And then we will say that if we assume that this we have tau number of them, these are the possible concurrent threads that can come and update the model from the time that you read until the time that you update the model. So what happens is that at the end, when you update the model, you're not going to update, in fact, the theta t model, but you're going to update the theta t plus tau model with your gradient. So because when you go and here when you update the model, then it's not anymore theta t. It's a different model. And this is an observation of looking when you look into the asynchronous parallel entities. That in fact a problem that happens is that you might have now let's see these tau processes that are shown here with black that have read theta 0, then and theta 0 here is the same with theta t in this example. Sorry for that. So they will do their calculations, and then they will work nicely and update the model going to the minimum. At the same time, there is also the R process here that has read theta t and then tries to update it, and the direction is good, but the problem is that once it comes and updates the model, it will update this theta t plus tau model. In this case, in fact, it will generate a noise that will make the process to go out of its convergence for a while. So the outcome of what I wanted to more or less say with that is that if you allow asynchrony, then you allow more noise to enter into the system. Then the computation does not conform to the sequential execution, and the good thing is that it reduces significantly the waiting time, because you can go and you don't have to wait, so you can go and do interesting work and useful work without having to wait. But on the other hand, there are a lot of issues that arise that are of interest for us to look. And the first thing is that if you look into these processes that are concurrently updating, we can call them stale processes. Then they generate what we call staleness or asynchrony or asynchrony-induced noise. So these processes, when for the process that process that reads and computes the new update, generates some noise, and the question is, how bad is this noise? And again, as I said, when we looked into the measures for computing looking into the efficiency of iterative methods like stochastic gradient descent, there are three parameters that you need to take care. One is the statistical efficiency, the other one is the time to convergence, and the other one is the computational efficiency. So we know that we will get computational efficiency. The question is that how good is it going to be on the statistical efficiency on the time to convergence, right? And when you look also into the asynchrony from the system's perspective, we introduce also some contention because of asynchrony on the read and update operations. And this is not that small. So we have also to look again, okay, we did this and we have asynchronous and asynchronous SDD. How much expensive is this read operation? How expensive is this update operation compared maybe to logs? Because there is going to be some contention here. How much time do I have?
Yeah, I just want a little bit of explanation on tau. Tau is what is it? What do you say is a kind of a error, or is it? Can you please repeat the tau? How philosophically what it is?
Tau measures the number of concurrent processes that can update the model from the time that you read the model until you update it. And in the worst case, you can think that tau is m-1. Mm-hmm. But you can also, I mean, as part of our research work and others, so then you can always also have a kind of an estimate of a tau based on the algorithm that you use. In this case, you can better estimate that if you assume some information, because you can think that in fact the worst case is this, but on the other hand, all these processes cannot be that in fact they finish at the same time, and yeah. So you can think that from the time that you read until you write, usually this is a time interval, and this time interval depends on the data. So it can be big or it can be small. So then the number of tau also can depend on that. Maybe I said too many things. So tau, is it clear though? But tau is the number of concurrent updates, the number of updates that can happen from the time that you read until you update the model. And in worst cases, m-1.
Okay.
How much time do I have? I think I'm running very slow. But is it 10 minutes more, or?
See
Satya, or?
Who keeps time? You know,
I'm keeping track.
Nikhil,
you have 20 more minutes.
I
have 20 minutes for presenting.
Yes.
Okay.
Is that enough, or you want more? Is that enough?
No, I think that's enough. Yeah. No, we'll see. It depends on the questions, but I think should be enough.
Yeah.
But thank you very much for the interactive part. I hope that everything is clear. That's I think the most interesting part.
And because of the questions, if we get delayed, you can take 10 minutes more because of the interruptions. We've been asking a lot of questions.
Yeah. Okay.
Sure. Yeah. Let us know. Okay. Go ahead. So,
yeah, as I wanted more or less to describe is that when you look into asynchrony, then there are a lot of questions that more or less are centered into these two big questions, or they're clustered in these two big questions. How does asynchronous staleness affect usually the convergence? That's one of the big issues. And then what is the impact of consistency that that inconsistent views from the model will on the again on the staleness of convergence, and on convergence, and what is also the impact of synchronization? Like as I said, now we have more contention on reads and writes, and this is what we are going to look a little bit now and try to see what I will try to show to you a couple of highlights of our work on that answer this question. And I will say a few things that are presented on the paper, consistent log-free parallel stochastic gradient descent of fast and for fast and stable convergence. And so when we did that, we also putting the things into context. Then in the literature, there is quite a lot of work on with empirical results and analytical results in the literature that look into asynchronous SDT, and all these results more or less seem very promising, and we more or less that is motivated us to look a little bit into that. So there is some work there, and we decided to go closer and look, and especially from the practical perspective. And what also we wanted to do is that we wanted to look into these kind of results also on the artificial neural network settings. That not a lot of things in this direction were there at that time. And when we're looking also into the research outside there, we realized that there is not a real framework, a unified framework that will allow you to compare one result with the other. So what we also, when we started doing this work, we started also thinking that we can start building a small framework that maybe other people can use also in order to make easier the comparison, and also help us to explore better and in a more consistent way the map of asynchronous SDT. And let's start with the first, as I said, we want to look into consistency, and one of the aspects, and let's see a little bit of how what is the situation when you are sharing state on an asynchronous SDT. So when you share the state, you are more or less using this read and update operations that will so what you have is that you have insert memory your model theta, and the easiest, the best way to share state is that you lock the state, and then you as an updater, you start updating the model into the memory after getting the log. So now, if a read wants to read the model, it has to lock and wait until you finish, right? And this is the standard, simplest way of implementing the asynchronous gradient descent. So then, back in 2011, there is a very well celebrated paper in asynchronous SDTs. They said, okay, what if I don't lock?
One interruption again. Sorry about that. But what exactly are you locking? You're locking theta.
You're lodging theta because you can think that if theta cannot be stored, it's a huge model, so it cannot be stored in one word. So you need to have a big chunk of memory where you store it, and so then when you want to write it, you need to lock and write all the components of theta.
So why is it called fine grained locking? So theta is it's a single element, right? So you lock, unlock, or so?
No, it is one big lock because you can think that you are updating the different parameters of your model. And yeah, we can see it now. So it is a very big lock, in fact.
So it's a coarse lock, not a fine grained lock, right?
Yeah.
Okay, fine. Thank you. Thank you.
So only one process can read and sorry, can write the theta, and you cannot read and write the theta at the same time. You can think that you can do some optimizations, but I think for the sake of this, this is only one lock. And there is a work that goes back to 2011 that in fact it is a very well celebrated paper where they said, okay, what happens if I take out the locks? Because in fact they observed that the locks slow down the processes quite significantly. Although it is asynchronous, still you allow only one process, one updater at a time, and when there is an updater, you don't allow reads. So this is a very well cited paper that is called Wild, and in fact, what happens is that then you can see that it will allow reads to take place concurrently with the writes. But then, when this happens, then this read operation here is going to read now a model that was not there. Was never computed because it will read these two blue parts of the new model and the white parts of the old model, and this was never a real model. But and then it will read it, take it, then take now the this part locally and compute the gradient descent. Generate the new theta and then go back and write it without locking, and then going and doing write its components separately. The nice thing is that you have good progress guarantees because here you can see that in fact here you don't lock. You have what they call this lock free. You are you go and you all the processes can go and progress without having to wait for the others. But on the other hand, you have very weak consistency. So what you are reading is not really that consistent. So they showed in the paper that in fact there is a very significant improvement on the performance. But on the other hand, this improvement comes on the sparse and convex problems. Because as you can think, if you have sparse and convex problems, then you don't update too many entries. So the probability that in fact this model that you have read is a real model then increases if it is sparse, because then you expect that maybe this blue were white anyway. Are you with me? So it works. It is inconsistent, but on the other hand, if you have sparse convex problems, then in fact the consistency doesn't show. You will not find it in practice.
So in other words, they're not taking a consistent snapshot. Can we say it that way?
Exactly. That's very correct. Yeah, that's exactly. Yeah. So, but it is simple and efficient, and there has been a lot of work in trying to analyze a little bit this behavior. So there has been a work by Desa and by Alistar, and in fact, Desa saw that in fact, because of this inconsistency, if you think that your model has d parameters, this hog wild way of doing things might require order of square root of d more rounds in order to converge. This is the worst case. And this is because of the inconsistent part. And then there is, and this was proven by Desa, and then by Alistar et al. They proved also that because of the asynchrony, because you are allowing to touch different models, and you have this tau on the computation that we saw before. Because of the asynchrony, you will have that. You might have also an extra order of tau rounds because of that, in order to converge in the worst case.
Just an interrupt, please. So in transactions, when they have that log-free transactions, so concurrent transactions, they use the timestamp concept. Do you have something like that here?
Yes, you can use the timestamp. You use the timestamps in order to identify, yes.
Okay.
Okay. And then you can think that, in fact, this t plus 1 or t plus tau plus 1 is the timestamp of the model that you have to generate. Yes. Yeah. So in fact, this is. Yeah. So what I want to say is that, in fact, that because of inconsistency, you have to pay this penalty. Because of asynchrony, you have to pay this penalty. And of course, the question is that, okay, if you pay this penalty, this extra round, do you get back what you pay, get more from the computational efficiency or not? And that's what we wanted to see, and we wanted to examine better. So, and then, as I said, if you look into the landscape, we have the log base where you're consistent, so you don't pay for this order square root of delta, but you pay for the log freedom. You pay for the asynchrony, and you pay for waiting on the log. And here, if you have hog wild, you pay the order this order square root of delta, but you have log freedom, so you don't pay for the log. You don't have convoy effects. So what we wanted, and I want to say a few things if I manage to find time. I want to talk a little bit about the work that we did, and that was led by these results on what we call least stochastic gradient descent, our work that try to be consistent so that we don't pay this order of square of delta. And then it is also log free so that we don't pay on convoy effects on the logs. So LIST stands for log free asynchronous shared memory entity. And it's a very simple algorithm, in fact. If you have studied log-free data structures, it looks like the universal construction of log-free data structure. So what we have is that we have a pointer that is only one pointer, and that points to the current model. So here I have that is stored in the shared memory. So I have the model theta t now, and the pointer says here is the current model. So let's take two processes that want to now to compute asynchronously and in a log-free way the HDD. So the processes have to first get the pointer and say, okay, here it is. And here I have my two processes. They both read the same model. Then one is they read A and they read B. And then they compute their, they select their mini batches. They compute the gradients, and then they don't copy as hog wild the model. They leave it on shared memory. They don't modify it. They do the computation, and as they do the computation, they generate now the new model that they want to produce and publish. So what they will do is that they want to publish the latest model, but then for consistency, we allow only one of them to do that. So that in fact, then we use compare and swap. So both of them will try to change the pointer to their own copy of the model, but one of them will succeed, the other one will not succeed because we'll detect that the pointer has changed. So now we'll have the theta plus 1 model for R1. And then the question is now for RA, sorry, what needs to be done for RB? And then what Liz does is that RB now reads the new model and doesn't try to and tries to now update with the new gradient and publish it and then change the other pointer here. Is it clear?
Yeah.
So you can think that we can generate, in order to go faster, also this with more processes. And if you look into the more processes, then you can think that when a process reads the model and then now tries to publish the new model, it can be that in fact the model has changed from theta t to theta t plus tau, what we said also before. So the model has changed quite a lot. And then based on our algorithm, then you have also to read this model and update now this model and publish now based on that model. So this is the basic algorithm that you can do. So you get the pointer, you compute, and you apply more or less the latest state in the new memory location by in a new memory location. Then you try to publish it using compare and swap. And then you're trying to publish that, and then you can think that as you try to publish that, you more or less execute a retry loop. You try until you succeed to fire the compare and swap. So this is a framework, the list framework. You can play with the algorithm, and then you can do a couple of things that we think they are important, and we also saw into the paper. One thing is that you can when you, let's say, see here that when you don't manage to file a successful compare and swap, you know that the model that it is there has been updated, right? So and then you can use the timestamp as you have already mentioned, and then by using the timestamp, you know what is the tau. So you have two choices also in this log-free, the listable framework. You have the choice to continue trying to get the retry loop, or you can, and if you do that, the nice thing is that you don't have to compute this, again, this gradient descent. This saves you time. But on the other hand, you know that you're pushing noise into the system, some noise, right? So it is up to also to the we allow also the possibility that the process can change and also maybe does not want to retry again, but starts again by reading. It is not on the slide, I'm just saying, and this is the adaptiveness that I will not cover. But another thing that I will cover now is that in fact, we also have as a kind of feature on the algorithm that when you retry using a strategy. That this is then you can think that you can parameterize the strategy. So that one strategy is that you don't retry again. When you see that the model has changed, you say, no, I don't want to have inconsistency, so I start again and I read. So we call this persistent 0, and then you can try only one time to change again you can do only one retry, trying to change the model to your model, or you can try for infinite times until you succeed. So the argument I showed to you here is where you are retrying forever is this PC infinity, but you can bound the number of retries on the algorithm, and we wanted to see how much this will influence. So do I have 10 minutes, or do I read it correctly?
So you're almost out of time. It's 1 hour. If you want, maybe, yeah, how much time do you need? Maybe 5 minutes?
Okay, 5 minutes or 5, 10? Can I take 10 or 5?
Maybe, yeah, 5 because there's okay. A break time, waiting to the break time.
Okay, good. So this is list, and it is the benefits that is log-free, and it provides an efficient reader operation. So we don't update this model. We only have the models when they're published only for read. And it uses it gives you also the opportunity to have a very nice memory recycling mechanism that can benefit sometimes. It might create some potential the retry loop, depending on how many retries you have, but then it is a knob that you can adjust in your system. So in the paper, we saw also how to compute the number of threads on the retry loop, so that you can, based on the ratio of the computational time divided by the update time. But I have to go faster. Okay, so we looked into the list, and then we wanted to say, okay, how does it work in practice? And we want to evaluate it compared to Hogwild, and also compared to the asynchronous log-based one. So we used MLP and CNN as applications with the MNIST image classification, and the MLP had 4 layers, and the number of parameters were 134,000, and for the CNN, the number of parameters were approximately 27,000 parameters. As I said, the parameters we use different step sizes and batch sizes on the paper, and also, but what I will talk about is that for the rest of the talk, the batch size is 512, and the step size is 0.005. Okay, so one thing that we saw is that. And this is for 50% training at the beginning. But when we look, is that we saw something that was also seen in practice. So that and this is for MLP. That in fact the stochastic gradient descent doesn't scale up to as many processes you want. So there is a sweet spot. In fact, you should go maybe for 16 in this particular setting. And what we saw is that the list worked good, and we more or less now will concentrate on 2 cases. And so, yeah, let me say that what we saw is that the list works quite well. And one thing that we noticed is that when it comes to stability, when it comes to convergence, it converges better compared to the other methods. And here we have, I saw how many executions we counted from the other methods that didn't converge or they crashed. So list looked okay. And of course, you can say that this is 50%, is not a representative, it's half, it's quite a big error. So I will go a little bit and look now into focus here into the 16 threads, which is the best number of threads cores to use for this particular problem. So what we see is that the list works quite well. It is competitive to Hogwild, and the nice thing is that it doesn't. It is more stable when it comes also to crosses and divergence. And if you want to push the communication into the extreme, if you want to have multi-threading, the other methods have big problems with instability, while list, because you control also the inconsistency, you don't end up with that. So it looks competitive to, as I said, to hog-wild, and in fact it gives better stability. And one thing that we saw in the paper is that also it is not affected that much on the parameter selection. And if I say a few things more, then what happens is that here I try to plot it, the tau value, the frequency of the tau value, the staleness. So if you take list with persistent 0, you will see that in fact the staleness that you experience in practice is small. Then this is a very nice control also knob that can help you with the consistency, and then the consistency will help you with the convergence. And here you see that in fact when you have list with persistency 1, then in fact the staleness distribution goes to the right, and while and the others have the same staleness distribution. So I need to conclude. So we see similar results, and in fact the interesting thing is maybe also that for CNNs, list looks to work better than hog-wild. In fact, it's quite significant improvement here, and you can see it also on the training convergence. So in fact, at least with persistence 0, when it is very consistent, it goes down to 0.5 error in 200 seconds, while if you go with hog-wild, you have to go to more than 300, which is 50% more. Okay, for CNNs, then it looks like it works much better. And when it comes to the memory consumption, also maybe I can go fast. For MLP, doesn't really change anything, but they change things on the for the CNN, and we also show into the paper why this is so. Because in CNNs, the time for computing is much more higher than the time for updates, and this is a place a significant role on the memory consumption. So, and to finalize, and as I said, we started implementing a kind of a framework for shared memory entities that it is outside there. We started implementing then our algorithms, and also having hog-wild and other algorithms. And we continue updating that. So we have different kind of logs that you can use. We have also read-write logs. We have different kinds of logs, and we also have other synchronization methods that we are adding in order to try to see what is the performance. And so you're welcome to add your algorithm there and try to use this framework in order to compare and understand the different methodologies for synchronous entity. And I think I will conclude here. I have to conclude. And I try to describe a little bit the landscape of the parallel stochastic gradient descent, and to look into the different parameters that play a significant role in the convergence of such algorithms, and show to you how we try to address the challenges with our list framework. And yeah, I think I should close here. and can open for questions. Thank you for listening, and thank you for also asking questions online.
Yeah.
On fly.
Thank you, Professor Philippas. So in the interest of time, we'll just have one or two questions, and then we don't have time.
Can I put a query? Just so in your log-free scheme, have you considered this fine-grained? You have sometime you talked about fine-grained consistency in the element. No, in this scheme, did you consider that also in your work?
Do you mean that the fine-grained accesses of the model, or?
Yeah, in model, when you have that multi-versions, you are taking it, probably, considering the fine-grained consistency, probably when a choice of maybe you can save some time or increase the parallelism, computational efficiency, or something. I was thinking, have you considered that? That's what.
No, in fact, we wanted to avoid that. So the scheme is using fine-grained synchronization on updating the full model, so you don't use logs.
Okay.
But on the other hand, we wanted to have that to read a consistent view of the model. The reason for that was that we wanted to look into CNNs and DNNs that are quite complex and they're not convex. And it has been shown that if you don't have sparsity and convexity, the log-free approach of hog-wild doesn't work. It produces quite a lot of noise. So because of that, we wanted to read a consistent model and to play only on when you want to update and your update is old with respect to the new state of the model. What shall you do? Our algorithm then allows you either update it or not update it, go back. And there is a kind of trade-off and then you can think that in fact now something that didn't have time to touch is that you can decide also on fly based on whether you would like to update even a newer model. You can decide based on the timestamp of that model and see, okay, how much different is it from my model, the model that I read? Is it 10 rounds after or 100 rounds? And then you can decide whether if you want to do it or not, and then or you would like to start again and read the model and continue from there. And there is a trade-off, because if you read the model and if you redo the computation, then you have to redo the computation. This is the expensive part. So the question is that, do you want to redo the computation or you want to apply the computation that you want to?
Okay. So if you fall into a trap of
I think,
Professor
Rishikesh, I think we're really short on time. The next is going to start in 6 minutes. So maybe we should give a break and we can take this offline.
Yeah, okay.
Yeah, so yeah, we are not on time. So thanks. Okay, we'll thank Professor Philippas Tsigas for a nice talk. Yeah, and we know that we interrupted him a lot during his talk. I hope with questions, I hope it is fine with him. Okay. Yeah, thank you. And